In the next few lectures, we turn to nonlinear systems of hyperbolic equations. And to start with, we're going to look at shock waves and something called the Hugoniot locus, which tells us what states can be connected to each other by shock waves satisfying the Rankine-Hugoniot condition. As an example, I'll use the shallow water equations. But let me also mention that this book, Riemann Problems and Jupyter Solutions, has additional information about solution of nonlinear Riemann problems, and in particular the shallow water equations that we'll be looking at has a notebook devoted to them that has a number of other illustrations, and we'll come back at the very end and look at one of those. So the shallow water equations in general model in one space dimension, they model the flow of water in a one-dimensional channel where the depth of the water is modeled by h, and u is a horizontal velocity. It's only a single velocity at each point x, which is a depth averaged velocity over the depth of the water. The shallow water equations are valid as a model typically when the wavelength of the waves that we're looking at is long relative to the fluid depth. But as we'll see, you can even use shock waves in the nonlinear shallow water equations as a model of a propagating bore, for example, in a shallow water flow. So the equations for the shallow water equations look very much like the equations of gas dynamics in a simple case. We're looking at conservation of mass and conservation of momentum. So the conservation of mass gives a conservation law for the depth h that looks exactly like the equation we have for the mass in gas dynamics. The flux of water is simply h times u at each point. And for the conservation of momentum hu, we have an equation that looks similar to the conservation of momentum in one dimension for a gas. Hu is the conserved quantity, and hu multiplied by u is the flux of that quantity due to simply advection. Any momentum that's in the fluid is being carried with the fluid downstream, so that gives the advective flux. But then there's another flux which corresponds to the pressure in gas dynamics, and here in shallow water equations it's the hydrostatic pressure. We're looking at the force of gravity. G is the gravitational constant, and then we can show that the hydrostatic pressure for a given depth is given by 1/2 gh squared. So this is exactly like the equations for gas dynamics. If you replace h by rho, the density, and replace the hydrostatic pressure by a simple equation of state that the pressure is a function only of density, then it has exactly the same form. And the Jacobian matrix is also similar. And the eigenvalues are, again, somewhat similar from gas dynamics. They look like u, the velocity, plus or minus the square root of gh in this case, which plays the role of the speed of sound in a gas. Here the square root of gh is the speed at which a gravity wave travels in fluid of depth h. And you can linearize these equations just like we linearize gas dynamics to get an analog of the acoustics equations that would model small perturbations in the surface propagating with speed given by the square root of gh for that background water depth. But here we're going to look now finally at the full nonlinear system of equations. And we know from looking at scalar equations that in the nonlinear case, we expect that if we start with even smooth initial data, it could develop shocks. So here, for example, if we start with a hump of water and let that flow outwards, so initially zero velocity, but some hump of water with gravity pushing down, then that's going to force two waves to move outwards. And initially they might look fairly smooth, but eventually they will sharpen up into discontinuities, shock waves, hydraulic jumps, followed by rarefaction waves. And each one of these propagating waves by itself, once they've separated for this particular simple initial condition, looks a lot like a solution of Berger's equation. Same sort of idea. But now we have two wave families, two nonlinear wave families, and for more complicated initial data, there would be some interaction between waves in the two families, and so it wouldn't look quite so simple as this. Also, if we let these shocks collide with each other or with other shocks, they wouldn't simply pass through each other the way they would in a linear acoustics problem, for example. Instead, you have nonlinear interaction of the discontinuities. So it's similar to the scalar case, except there's two distinct families, and they can also interact with each other. So again, we'll kind of simplify things by looking at the Riemann problem as a first example, and concentrate a lot on how to look at shock waves in the context of Riemann problems in this lecture. So for the shallow water equations, one particular Riemann problem is what's called the dam break problem. This refers to the case where the velocity is zero in both the left and right states, and we just have a jump in depth as if there were a dam here, and then at some point we break the dam and we let the water flow, and it turns out what you sort of expect physically is that you're going to get water flowing from left to right, and in fact what you see is mathematically is a shock wave that propagates from left to right in one of the characteristic families, but then you also have a rarefaction wave that's traveling from right to left in the other direction, in which the fluid is being accelerated. So we have these sort of, in this particular Riemann problem, with this particular data, you actually have one shock wave and one Riemann, or one rarefaction wave coming out of the Riemann solution. Depending on the initial data, you could have two shock waves or two rarefaction waves, and we'll look at some other cases later. Here I should say the color is just a passive tracer. So I started out back at the beginning with red fluid to the left of the dam, blue fluid to the right, and these stripes are just help you sort of visualize how things move. You can actually solve for the, say, the concentration of some dye in conjunction with this if we added another equation to the system for an advected quantity that measures the color of the water. And then if you color the water according to that, then you can see that what happens is that the fluid is being accelerated to the right in between both the shock wave and the rarefaction wave. And you can see that there's also a what's we'll call a contact discontinuity, especially when we get the gas dynamics here, where the red fluid that was initially to the left of the dam and the blue fluid to the right are in contact with each other, and that discontinuity is moving at the fluid velocity in between the shock and rarefaction wave. Here's another Riemann problem where you end up with a different structure in the solution. In this case, I'm using a slightly different color scheme, but again, there's an interface here where we have paler blue on the left and darker blue colors on the right. But I've taken initial data so the depth is the same on both sides, but there's a jump in the velocity. So the velocity is +1 on the left, but -1 on the right. And that means that this fluid is moving towards this interface from both sides. And then what happens as you go forward in time is as these two streams of water collide, you end up with water building up in the center, and you end up with two shock waves that move out. And in this case, because I took equal and opposite velocities and the same fluid depth, you get a very symmetric picture where the velocity in the middle state is 0, and the depth is some higher value, and you have two equal strength shock waves moving in the two directions. Here's a couple other pictures of that same case, and in particular down here on the bottom right, I'm showing the particle paths in the xt plane. So this is again the t direction, and these are the two shock waves. And then the other curves here are how particles of water would be moving. So water that starts out over here is moving to the right, but as the shock wave passes by, the velocity becomes 0, and so that particle stops. After the shock wave has passed by, it's moving with speed 0. Similarly, a particle that starts to the right is moving to the left until the shock wave passes by, and then it has stopped and has velocity 0. So you have particle paths that look like this, with this 0 velocity in between the two shock waves and a higher depth in between the two shock waves. This is actually the height over here on the right, I guess, but we can also look at the vertically integrated pressure, the hydrostatic pressure, and that also is higher in the middle than in between the shock waves than on either side. Now, in addition to looking at particle paths, it's also very useful to look at characteristics when we talk about shocks versus rarefactions. We know we have to look at characteristics to see whether they're impinging on a shock or spreading out. And just to remind you that for a scalar nonlinear problem, if we write the equation in quasi-linear form, qt plus f prime of q qx equals 0, and assume that the solutions are smooth, then we can find these curves x of t. If we can find a curve that satisfies an equation of this form, x prime, the slope, speed at which it's propagating, is equal to f prime evaluated at q at that same point, x of t, at time t, then if we differentiate q of x of t, t along that curve, then the time derivative we can write as the x derivative times x prime of t plus the t derivative. But if this equation here is satisfied and we use that here, then because of the quasi-linear form, we end up with this just being 0. And so for a scalar equation, what we see is that if we can identify these curves, that q is then constant along each characteristic curve. The time derivative, total time derivative of q along a characteristic curve is 0. And moreover, because the slope of these characteristics, or the speed at which they're going, is exactly f prime of q evaluated on the characteristic, if q is constant on the characteristic, then so is the speed x prime of t. And so these characteristic curves must in fact be straight lines in the xt plane. And they're just rays that start at some point and move at constant speed. In the case of advection equation, the linear equation, they all have exactly the same slope u, and so they're all parallel straight lines. In the nonlinear case, though, the characteristics may be either converging or diverging. If they're diverging, then we have a rarefaction wave sort of situation, but if they're converging, then eventually they may cross, at which point we have a shock forming instead. So that's the familiar case for the scalar problem. We can look at something similar for nonlinear systems. Again, we can write it in quasi-linear form, and then look at the eigenvalues and eigenvectors of the Jacobian matrix. So if f prime of q times a vector rp of q is equal to a scalar lambda p of q times rp of q, then rp is an eigenvector of the matrix, and we've defined the problem to be hyperbolic as long as we can always find a linearly independent set of eigenvectors, m of them for an m by m system, with eigenvalues lambda p that are real numbers. Then it's a hyperbolic problem. And we can use that to define characteristic curves in the nonlinear system case. And it's maybe easiest to think about this in the case where we have things that are a wave like on that first picture we were looking at, where the hump of water in the shallow water equation split up into two simple waves, one moving in each direction, that looked like solutions of scalar equations. And you can study one of those waves in isolation by choosing initial conditions q of x at time 0 in such a way that its variation, or its derivative, is a scalar multiple of the right eigenvector rp evaluated at the corresponding q of x. So if you can somehow set initial conditions so that it's everywhere a scalar multiple of an eigenvector in the pth family, then we can work out how the solution behaves along a characteristic curve that's, again, just as in the scalar case, some smooth curve capital X of t, along which we'll see that the solution in this case can be actually constant. So we can compute that along curve x of t, again, if we differentiate with respect to time, q of x of t, then t appears two places here, so we get the x prime of t times qx and plus qt. And then qt, using the quasi-linear form of the equations, qt is minus f prime of q times qx. And then by my assumption up here that qx is just a scalar multiple of the eigenvector rp, we can write this, the qx here is just wp times rp, and the qx over here as so WP times RP. And since WP is a scalar, I've pulled it out in front of the Jacobian matrix F prime here, for example. So we get this form. And now, if we look at this, we can actually set this to 0 in order to get a curve along which Q is constant again. And if we set this to 0, then we can cancel out the WP, which is the same in both places. And what we see is that we require that F prime of Q times RP at the same Q is equal to X prime times RP. And X prime is the characteristic speed. And we can make this be 0 simply by taking X prime of t to be the corresponding eigenvalue at this particular state. So the upshot is that if we have initial condition of this particular form, and if we look at a curve x of t along which x prime of t is the eigenvalue lambda p corresponding to this eigenvector rp that we've used to choose our initial data, then this total time derivative of q along the characteristic is equal to 0, just as in the scalar case. And again, because the value of q is equal to 0, that means the value of the eigenvalue lambda p of q is going to be constant along this characteristic. And so x prime of t is a constant along this characteristic, and therefore, again, it's a straight line. So in the case of a simple wave, q of xt is constant along each ray with x prime equal to lambda p, the eigenvalue evaluated at that state q. And as long as these characteristics don't cross, then the solution would simply be constant along each of these lines. In this particular special case where we have a simple wave. It gets much more complicated when you have a variation in all of the characteristic families, but still we need to sort of identify what we mean by the characteristics around an isolated shock, for example, and this is the idea. It allows us to go from the notion of characteristics in the linear case directly to the system case. So if we go back to that example we were looking at of the flow impinging on the initial discontinuity from both sides, and you get two shocks moving out, one to the right and one to the left, then we can work out what the characteristics are. For the shallow water equations, they're exactly the curves x prime of t is equal to one of the eigenvalues, and the eigenvalues are u plus or minus the square root of gh. So in regions where u and h are constant, x prime of t is constant, and it's just either u minus the square root of gh or u plus the square root of gh. Those are the two characteristic speeds. And so we have, in the case of a Riemann problem where we have a state q left over here and a state q right over here, away from this discontinuity at least, we have simply two characteristic speeds. The one characteristic, which is lambda 1 equals u minus the square root of gh, and the two characteristic, which is lambda 2 equals u plus the square root of gh. And if we plot those, for the case I gave, lambda 1 is actually equal to 0 in the left state, so the characteristics are simply moving like this. But in the right state, lambda 1 was negative, and the characteristics are moving like this. Now, as the characteristics cross this shock in the second family, they simply change direction because the middle state up here, qm, is different from q right. And so when we evaluate the characteristic speed using um minus the square root of ghm, that will be different than ur minus square root of ghr. And so there's a kink in the characteristic here. But then it moves along at constant speed again based on this middle state. But now we see that it's converging on the shock, as are the characteristics coming from the left. So this is a shock in the one family that satisfies the lax entropy condition that the characteristics for that corresponding family are impinging on this discontinuity as time advances. The other eigenvalue, u plus the square root of gh, On the other hand, again, it's constant in the right state, and in this particular example, the characteristic speed is 0 in the right state, but it's positive in the left state. And again, it changes slightly as it goes across the one shock, but it continues moving to the right, and it impinges on this shock, as do the characteristics in the 2 family on the right side. So again, these lines I've drawn here are lines x prime of t equals lambda 2, whereas on the left they were x prime of t equals lambda 1. Now we've also already looked at the conditions that have to be satisfied across a shock wave, the Rankine-Hugoniot conditions that we derived by integrating the conservation law. If we have a shock moving at some speed, and we looked at our conservation law, and the states were just q left everywhere to the left of it and q right everywhere to the right of it as the shock is propagating in this direction, then by integrating the conservation law around this rectangle, we found that the jump in F, the jump in the flux between the right state and the left state, integrating along these 2 sides, had to be related to the jump in Q on the top and the bottom, and the speed at which this shock is moving by this Rankine-Hugoniot condition. And for the scalar problem, the jump in Q and the jump in F were scalars, so we could solve for S by simply dividing. But now we're looking at systems, and so this relation only holds for certain vectors, QR minus QL, because S has to be a scalar. That's the shock speed. And we've seen this already for a linear system. In that case, F is A times Q, so the jump in F is A times the jump in Q. And so this says that A times the jump in Q has to be a scalar multiple of the jump in Q, and so the jump in Q has to be an eigenvector of the matrix A, which is the Jacobian of the flux in the linear case. And in the linear case, what we saw was that if we look at phase space, that through any given point, assuming it's hyperbolic, there are m different rays that pass through that point, given by the m different eigenvectors of the matrix A. And if you fixed one state and then took some other state that was anywhere on one of those rays, then you could connect those 2 states by a single discontinuity, propagating with a speed that's given by whatever eigenvalue is associated with the eigenvector that you moved along. And those rays would simply be straight lines in the linear case. Now for nonlinear systems, we'll see that something similar happens in phase space, except that through each point we'll have m curves that won't simply be straight lines because of the nonlinearity. As you change q, the characteristic speeds, the lambdas change, and the eigenvectors also change, and so you don't have a single eigenvalue and a single eigenvector that you can simply translate to any point in phase space. You have to find these curves, and these curves are what are called the Hugoniot loci. Loci is just a set of points that satisfy this Rankine-Hugoniot condition. If we fix one point and then look at what other points can we connect to it in phase space with this Rankine-Hugoniot condition being satisfied for some scalar S. So let's work this out for the shallow water equations. That's the best way to sort of understand what we have to impose in order to figure out what these Hugoniot loci look like. So here I'm going to fix one particular state that I'll call Q star. It could be the left state or the right state in the Riemann problem, for example. But based on this one Q star, I want to find all the other states in phase space, in HU space, in this case, that we can connect to that state by a shock wave or a discontinuity that satisfies the Rankine-Hugoniot condition. And here I'm looking at, I guess the phase space here, I'm looking at HU rather than H and HU. You can do this in terms of H and momentum, but it's a little easier often to think of it in terms of depth and velocity, sort of primitive variables, the natural variables we might want to be plotting. So again, this is the Q and F for the shallow water equations. And now we're asking what states Q, and we want to find sort of the equation for all possible states Q that we can connect to this fixed state Q star by a single discontinuity, by an isolated shock. Although we haven't yet said anything about entropy conditions, and so when we impose the Rankine-Hugoniot condition, that's not necessarily giving us a valid entropy satisfying shock wave. Just as in the scalar case, we'll also have to worry about whether it really should be a shock wave or should there be a rarefaction wave instead. But to start with, we'll just impose the condition that what states can we connect to Q star by a discontinuity that satisfies the Rankine-Hugoniot condition, which again is written here. Or in terms of the two components, S times the jump in Q is S times the jump in H, and S times the jump in HU. And on the right, we have the jump in the flux, HU, and the jump in the momentum flux, HU squared plus a half GH squared. And so when we do that, we end up with two equations that have to be satisfied in order for the Rankine-Hugoniot conditions to be satisfied. But there are three unknowns, H, U, and speed S. So again, we fixed Q star, but we're looking for H and U, and also the speed S is an unknown here. And as we vary the state Q, S will be changing along with H and HU. So that suggests, since we have two equations but three unknowns, that suggests we might be able to find a one parameter family of solutions, and those are the curves of points that can be connected to Q star. And so here again are the Rankine-Hugoniot conditions, and we can solve these equations for U as a function of H and S as a function of H. If you just manipulate these, and since they're two equations but three unknowns, we can write solutions U as a function of the parameter H, and we can parameterize S in terms of the parameter H. So for example, this equation for S simply comes from dividing in the top equation, dividing the right-hand side by the left-hand side. And then once you have S, if you plug that in here and solve for HU and divide by H, you get this expression for U. So I'm skipping some details here, but you can derive those expressions for how U and S vary with H. So again, we're thinking of H star and U star as being some fixed point in phase space, but now we want to vary H away from H star, and this tells us how U has to vary away from U star. In fact, we see that U is U star plus or minus some quantity that vanishes as H approaches H star. So as H moves away from H star, U moves away from U star. And in this equation, we see that there's a plus or minus sign here. And that's because we expect two different curves through any given point, one corresponding to lambda 1, which is U minus the square root of GH, one corresponding to lambda 2, U plus the square root of GH. And we see similar sort of expressions here for how U varies along each of those two curves. If we sort of parameterize these states by saying that H is H star plus some alpha, then as alpha approaches 0, H is approaching H star. And we can rewrite the expression for U and H. We can combine to see that HU is equal to the momentum H star U star at this point we chose, plus alpha times this expression. And therefore, you can look at H and HU at a neighboring point as being H star, HU star plus alpha times a vector. And as alpha goes to 0, of course, HHU is approaching H star, U star, but also we see that this variation for small alpha is proportional to the vector 1 and U plus or minus the square root of GH star as these order alpha terms vanish. And these are exactly the two eigenvectors, R1 and R2, corresponding to the minus sign and the plus sign, R1 and R2 are exactly the vectors 1, u plus or minus square root of GH. So what that's telling us is that near this point H star U star, the points nearby that we can connect to that state lie along curves that are tangent to the eigenvector directions. So they're tangent to the eigenvectors of the Jacobian matrix. Now, of course, in the linear case, they were exactly in the directions given by the eigenvectors, and you could go arbitrarily far and just move in that one direction because the eigenvalues and eigenvectors never changed. But in the nonlinear case, the eigenvalues and vectors vary as you move away from the point Q star. But at the point Q star, the direction to move in to satisfy the Rankine-Hugoniot condition is the directions given by the eigenvectors, and the curve of all such variations are tangent to the eigenvectors at the point U star Q star. So here's a picture. In this case, it's in the HU plane, and I've taken a single point here, which is our Q star, and then we ask, which states can we possibly connect to that by a discontinuity satisfying the Rankine-Hugoniot condition? It might not be a physically correct shock, but I'll call it a shock in quotes if it satisfies the Rankine-Hugoniot condition. And what we saw is that there are two families of solutions, two curves of solutions that we can connect. And if I drew tangent lines here, those directions would be in the directions R1 and R2, and that allows us to label one of these curves, the blue one in this case, as the one wave locus, and the other curve, the one that's tangent to R2 at this point Q star, we call the two wave locus. So these are the Hugoniot loci. These are all the points in phase space that can possibly be connected to this point Q star by a jump discontinuity satisfying the Rankine-Hugoniot conditions. And we have two families of them because it's a system of two equations. But the fact that it's a hyperbolic system means the Jacobian has a complete set of eigenvectors, so the two directions R1 and R2 have to be linearly independent, and we can find two distinct families of curves. So now we can look at trying to solve a Riemann problem. What do we do if we have two different states and we want to find a pair of discontinuities, a pair of shock waves that connect those two states, as we did in the system of acoustics, for example, in the linear case? If we have a left state and the right state, then we might hope to find two waves with some intermediate state QM in between. And in the linear case, what we saw was that QM minus QL, the jump across this wave, has to be an eigenvector proportional to R1, and the jump QR minus QM has to be an eigenvector proportional to R2. In the nonlinear case, the same sort of thing is true, except that now we need QM and QL to lie on the same one-wave locus, and we need QM and QR to lie on the same two-wave locus. So if I choose points QL and QR in the plane, what's the intermediate state? Well, it depends on which one of these points is Q left and which one is Q right, because just as in the linear case, in this picture in the XT plane, in order for the one wave and the two wave to be separating like this, we need the left-going wave to be moving at speed x prime equals lambda 1, while the right-going wave is moving at x prime equals lambda 2. And so we have to have QL and QM connected by a one wave, QM and QR connected by a two wave. So for example, if I take QL to be this state and QR to be this state, then from QL we have to move along the one wave locus, and QM can be anywhere on that curve. But from QM to QR, that has to lie along the two wave locus through QR. So QM also has to lie on this set of points that we can connect to QR by a two wave. And so there's only one possible point that QM can be, and that would be down here in this case. But if we switch those two states, QL and QR, then in this case, from the left state, we have to move along the one-wave locus again to get to QM, and then along the two-wave locus of QR to get from the middle state to QR. So where the intermediate state is, just as in the linear case, depends on what order these states are in. And we always move first along the one-wave locus and then along the two-wave locus. And if we have a larger system of 3 equations, then it becomes much harder to draw, but that would be the same idea. You need to move along the one-wave locus from QL to some state, and then along a two-wave locus to another state, and then along 3-wave locus to the right state. So if we assume that the Riemann problem we're looking at for shallow water equations can be solved with 2 shocks, then we can always sort of construct that intermediate state as we just laid out graphically, or in terms of the equations. If we look at the equations that have to be satisfied along these Hugoniot loci, along the two-wave locus, we have that the velocity u is ur plus something, whereas along the one-wave locus, states have to have u connected to ul by a similar expression, but with a minus sign. So the state um that we're looking for has to lie on both of these curves, so it has to satisfy both of these equations simultaneously. So if you just eliminate um and set these two equal to each other, then you can solve for hm. You now have just one unknown in this equation, hm. We know hl and hr, ul and ur, and you can solve that equation for hm. It's a nonlinear equation, but you can use some nonlinear equation solver, and that gives you the solution of the Riemann problem. So assuming that what we really should have is 2 shock waves, and we'll look more next time at rarefaction waves. But here's just kind of an indication of how we look at whether a shock wave is satisfying the entropy condition or not in this case. What we have, remember, if we have a physically relevant shock wave, say in the one-wave family, then what we expect is the characteristics are impinging on that shock from both sides. The one characteristics, that is the curves along which x prime is lambda 1 of q for the states ql and qr. And so if we have a point, some particular point that we're looking at, q star again, and we look at this blue curve is again the set of all points that could be connected to that point with a one wave that satisfies the Rankine-Hugoniot conditions. But now we look at the question of, if we do connect to that, are the characteristic speeds impinging on it from both sides, or are we in a situation where maybe the characteristic speeds are moving outwards on both sides, and this shouldn't be a shock wave, it should really be replaced by a rarefaction wave. So that depends on how lambda 1, which is the speed of these characteristics, varies in the phase plane. So again, it's much more complicated than in the scalar case. So the green curves here are actually contours of lambda 1. Lambda 1, remember, is a function of q. So this is our phase space, the first component of q versus the second component. So lambda 1 is varying in this phase space. And for the particular point I chose here that's circled, lambda 1 happens to be equal to 0 at that state. But as we move along this Hugoniot locus corresponding to one waves in this direction, we find that lambda 1 is decreasing to -1 and then to -2. Whereas if we move in the other direction along this same Hugoniot locus, then it would be increasing. It goes from 0 to lambda equals 1 and then lambda equals 2. And so if we're trying to decide whether a discontinuity between this point and some other point on this Hugoniot locus is admissible or not, we want to look at how does lambda 1 vary between the two states. Is it decreasing so that we're in a situation where the characteristics are impinging on the discontinuity, or is lambda 1 increasing as we move from the left state to the right state, in which case this is not the correct entropy solution, and we should be using a rarefaction wave instead. So that sort of picture indicates that for a given point, again, it depends on whether we're thinking of that point as being the left state or the right state. So it's hard to read here, but this it says QL. So if you think of this point as being the left state, and then you ask what points along this Hugoniot locus can be the right state, well, you can choose points down here on the solid portion of this curve, and that jump discontinuity will have characteristics in the one family that are impinging on it. Whereas if I chose a point over here on the dashed portion as my QR, then the characteristic speed would be increasing from QL to a point like this, and therefore it wouldn't satisfy the lax entropy condition. So only along the solid portion of this curve do we have entropy satisfying shock waves. Conversely, if we look at two shocks, and now we're trying to maybe find a state that's connected to QR, if we're looking for an intermediate state in a Riemann solution, we want to connect QR to a middle state. In that case, what we find by similar analysis, looking at how lambda 2 varies, is that we would have to take our left state or the middle state if we're trying to solve a Riemann problem. Whatever's connected to QR by a 2 shock would have to lie up here on the solid portion. And this portion of the curve down here where it's dashed corresponds to states that can be connected to this QR by a discontinuity that satisfies the Rankine-Hugoniot condition, but it does not satisfy the entropy condition. So to solve the Riemann problem, we can sort of put these two things together. So if we look at this case we had where the fluid is impinging from both sides with the same depth on both sides, and so I claimed that the right solution was two shock waves moving outwards with some middle state in between, then that is exactly this sort of situation where the middle state can be simultaneously connected to the left state with a shock and also to the right state with a 2 shock, because in this case Q left has some value of the depth and some positive momentum, whereas QR has in this case the same depth but a negative momentum, the negative of QL. So sorry, this is QL and QR here. And so we can move from QL along the one-wave locus on the solid portion of the one-wave locus, and we can move from QR along the solid portion of the two-wave locus until we get to this intersection point, which is QM, the middle state. And because we can find an intersection of those two loci that lies on the solid portion of both those curves, we know the correct solution is in fact 2 shocks coming out of the Riemann solution. And here again is the picture of how those characteristic curves look, and they are indeed impinging on both of those shocks. Yeah, and here again is the sort of animation of how that evolves. And here's another example where you also have a 2-shock solution. You don't necessarily have to have exactly the same depths and equal and opposite velocities. Here I've chosen different depths initially, but I've still chosen the velocity to be positive on the left and negative on the right, so that the flow is impinging on each other. And so what you get as you let time evolve is again a higher intermediate state and 2 outward going shocks, although in this case the velocity in between is not 0 because it wasn't completely symmetric. So again, the picture on the left was a case where we have 2 shocks in the Riemann solution is the correct Riemann solution, but if we go back to the dam break problem that I showed at the very beginning, that was a situation where the left state had one depth and the right state had a smaller depth. So HR was greater than HL, and the velocity was initially 0 in both states. So they both lie along the HU equals 0 line. So they're oriented this way in the phase plane. And now if we try to use the Hugoniot loci to find a solution of the Riemann problem, we would have to move in this direction from QL and in this direction from QR in order to find our intermediate state QM. And now we see that the jump from QL to QM is lying along this dashed line, and it's indicating that although there is a discontinuity, there's a solution that consists of two discontinuities satisfying the Rankine-Hugoniot conditions, but one of them does not satisfy the entropy condition in this case. And if we draw the characteristics, if we compute what the shock speeds are, assuming that they were both shocks, and then draw the characteristics, then we see a very different picture than before. The two-wave in the picture I just showed you did look like an entropy satisfying shock, and the characteristics are impinging on the shock, but the one wave did not, and the characteristic speeds actually increasing as you go across the one wave. The characteristic speed lambda1 is increasing, and so things are spreading out here instead of impinging on the shock. So again, the correct solution for the dam break problem looks more like this. It has a shock wave in the two-wave family, the one moving to the right, but in the one-wave family, it should really be a rarefaction wave. The fluid accelerates smoothly on the left, and in order to completely properly solve this Riemann problem, next we need to look at how do we find states that can be connected through rarefaction waves rather than shock waves. And we'll find there's actually a different set of curves in the phase plane that connect a point with other points by rarefaction waves. So again, it's more complicated than the scalar case, and we'll take that up in the next lecture. But let me again remind you that there's a shallow water notebook in this book that talks more about the Riemann problem. And also in that notebook, and also on this web page here, which is just the main web page for the book, if you go down to the bottom, you find a little JavaScript application that allows you to explore this Riemann solution for the shallow water equations. So this is a Riemann problem where the solution consists of two shocks, and as time advances we have two shocks moving out, but you can take the left and right states and move them around in the phase plane and see how the Riemann solution changes. So there's a wide range of possible states for which the two-shock solution is correct, but at some point, depending on how you choose your initial data, you might have instead a rarefaction wave and a shock, or you might have a rarefaction wave in the other family, or you could even have rarefaction waves in both families. So to understand the full solution of the Riemann problem, we have to get into understanding how to construct the curves that connect states with rarefaction waves.